I mean, you can see it on the screen and you can see it on my presentation also. I work for Furnace Improvement Services in US. And today we are conducting this webinar on a very important topic. The topic is your fired heater pressure drop limited? And the reason we are doing this webinar today is because recently we did two cases, two clients came to us and told us that their heaters are pressure drop limited and they want our help in reducing the pressure drop. So we worked with them and we came up with the new scheme, and that's what we want to show it to you today about how we can reduce the pressure drop across fired heaters by using our split flow process, which is a patented process. And that's what we will be talking about this morning or this evening. Uh, I think most of you know me. I graduated in chemical engineering from IIT Kanpur in 1974. And next year, I'll be completing 50 years continuous working. Currently, I'm working as solution provider with Furnace Improvements. I am supported by a very good team of 40 engineers in our Noida office. They help me every day to work on the presentations, doing this webinar, organizing the webinar. So I want to thank you before I start the webinar to my very able team for helping me out and working on this presentation. So why are we doing this webinar? And the reason is Furnace Improvements is a very small company and we don't have the means of advertising in big journals, magazines, or putting ads. So we resort to participation in conferences and doing webinars because we want to show to you what we have done in the past 27 years. Furnace Improvements started in 1996. And I want to tell you how I started Furnace Improvements. I used to work in a heater company and we were going in Texas City in Houston. And Texas City has 6 refineries, so it's almost a very high concentration. I was talking to my sales manager and I asked him, Bob, who takes care of these furnaces? And he said, no one. So couple of years down the road, when the opportunity came for me to change my career path, I thought everybody is working on new furnaces. Why don't we start working on existing furnaces? And that is how Furnace Improvements was born. We started in 1996, opened an office in India in 2005. It's been working there for almost 18 years. And our focus has been improving the performance of existing heaters. We have worked on boilers also. Our model is working directly with the patient. We work directly with the end users, owners, operators. And every time we work with them, we try to provide value-added solutions, unique value-added solutions. And because of our presence in India and US, we are practically working around the clock, almost 24 hours a day. We are able to keep schedules. Our philosophy has been high quality technical work and do it once, do it right. Before we take a project, we do a preliminary assessment and want to make sure that we have a solution, at least some framework of the solution. So we make sure that we do it once, do it right, so you get the best from us. This is a list of our clients in the past 27 years. We have been working with Phillips 66 for more than 20 years now, and 70% of our revenue comes from Phillips 66 for the past 10 years. We have also worked with Citco. Citco gave us a lot of opportunities. They were our first clients. They We installed the first split flow at Citco. We have worked, we supplied them the first heater, so we are very indebted to Citco also. And then we have Delec, Valero, Lion Oil, Country Mark. Most of the work we do is coming from a few clients. We are such a small company that we prefer working with only few clients. We have worked with Lyondell Bessel in India. We have worked with HP. Uh, we have done some work for MCF recently. We have done some training for Reliance. And currently we are supplying a crude heater in Jamaica at Petrojam. So these are, I want to take this opportunity to thank all my clients for giving us an opportunity to serve them and provide unique value-added solutions. Now, as I said, we have focused on revamping heaters or working on existing heaters. So why did we do that? Because everybody else was focused on working on new heaters. So we found a business opportunity. And then we also have a little bit of contrarian approach. We started and we thought, hey, let us do something new. And that pursuit led us to filing of 3 patents, 3 technologies. The first one was split flow technology. And we did this for Citco because Citco wanted to increase the efficiency and reduce NOx of a platformer heater. And we were able to execute the project for 50% of the cost. So that's how we got this. The second technology what we have is inclined firing technology. It's very, very simple. We put burners at about 3 to 7 degree angle on away from the tubes. And this again came because Citco had a crude heater where they were experiencing tube ruptures. They had 2 tube ruptures in 3 years. They came to us. All we did was we took their existing burners and put them in an inclined fashion. And that extended their run length to almost like 5 to 6 years. Our latest patent and technology is on smart dampers. We found that existing dampers, because of so many reasons, are not able to control the stack draft. And we keep on blaming operators or we keep on blaming the designs. So we found that you need a smart damper to control the draft effectively. And now we are putting smart dampers in all our fired heaters. We are putting inclined firing technology in all our new heaters. So the contrarian approach has helped them. We have challenged the conventional wisdom, and we have been successful most of the time. Not all the time, but most of the time we have been successful. So with that, let's move on. So today's agenda is talk about pressure drop, how to reduce pressure drop across heaters. I've got 3 case studies. Let me see if I can finish all the 3 case studies and questions and answers. If I'm not able to uh, answer your questions, please still send it to me and I will answer it to you individually. So let's talk about the importance of pressure drop. I know all of you have been operating fired heaters, but I have been designing fired heaters for you. And there are three important parameters whenever you design fired heater. The first one is the thermal efficiency. You set how much thermal efficiency you want to achieve, maybe 90%, 92%, 95% is also generally not possible, but we are trying. And once you set the thermal efficiency, it dictates the flue gas temperature leaving the stack, and designers uh, proceeds, whether they have to put an air preheater, whether they have to put a waste heat boiler. So thermal efficiency is an important parameter. Another important parameter in fired heater is the radiant heat flux. It basically dictates heat transfer per unit area. And a good number is 10,000 radiant heat flux. You can go to 12,000, but you will end up paying in terms of run length. But radiant heat flux is a very important parameter. If you're comparing two quotations, make sure they have the same radiant heat flux, because it also affects the cost of the heater, the size of the heater, so many parameters it affects. The third is pressure drop, and that's what we are talking about. Because pressure drop dictates the tube size, number of passes, mass velocity of the fluid or linear velocity of the fluid, film temperature, and coking rate. So you can see pressure drop is a very, very important parameter. So how do we decide pressure drop? This is the first parameter when the process engineers are designing your plant, or the process licensor is designing your plant or preparing a flow sheet. They will, based on their experience, based on vendors' recommendations, based on heat transfer experts' guidance, they will set a number. And they will use that number to size their charge pumps or compressors in case of reformer heaters. So pressure drop, once selected, cannot be changed unless the charge pump has a margin. You end up putting a bigger impeller, putting a larger motor, and all those things are very expensive. I mean, it can be done. It is not that it cannot be done, but all those things are expensive. So pressure drop is a very important parameter. If you are in project engineer, if you want to specify the pressure drop, I have some guidelines for you, but please make sure that these are general guidelines. For crude heater, we normally go with 150, vacuum 50 to 100, catalytic reformers or platformers 3 to 5 psi per pass. If you are doing a feed preheater or reboilers, general value is 50 psi. Delayed coker goes 300 to 450 psi, and whiz breaker is about 300 psi. So these are just general recommendations. The licensor will give you specific recommendations in terms of mass velocity. The vendors will tell you, how much pressure drop they can do. But what I'm trying to tell you is pressure drop is a very important parameter. So why do you get limited on pressure drop? When you increase the charge rate, that's more common thing, that when you increase the charge rate, you will get pressure drop limitation. If you change the operating conditions, like increasing the outlet temperature, increasing outlet vaporization, or if you have a change of crude or feedstock, a lot of times coking or fouling of tubes will also increase your pressure drop. Those are typically known as end of the run pressure drops. And anytime your pressure drop limited, you will be limited on the charge rate or on your profits directly. So pressure drop limiting is a very important thing. And we have worked out a solution for how to lower the pressure drop. So I'm not trying to be too technical, but I just want to give you three parameters what dictate the pressure drop. And pressure drop is proportional to the mass velocity of the fluid, or you can also take it as a linear velocity of the fluid. Pressure drop is inversely proportional to the tube diameter and directly proportional to the tube length. So pressure drop increases as a square of linear velocity or as a square of mass velocity. So if you double the charge rate, your pressure drop will go up 4 times. If you increase it by 20%, your pressure drop will go up by 44%. So if you want to reduce the fluid velocity, pressure drop will come down. So if you reduce the velocity by 50% by doubling the number of passes, your pressure drop will go down by 70%, so it will be 1/4. So these are very simple thumb rules, and what basically comprises of the pressure drop. So pressure drop is proportional to the length of the tube. I mean, depending on the length of the pass. So if we reduce the length of the pass, pressure drop will come down. Or pressure drop is inversely proportional to the tube diameter. So smaller the tube diameter, more will be pressure drop. Larger the tube diameter, less will be pressure drop, assuming that the mass velocity and length is the same. So that is three parameters which dictate the pressure drop. And a little bit more before we go into uh, details, uh, because most of you are from refinery background and their coking rate and film temperatures do play an important role. So I want to talk to you about heat transfer coefficient. Heat transfer coefficient is proportional to the mass velocity raised to the power 0.8, and film temperature rise is directly proportional or inversely proportional to the heat transfer coefficient. And anytime you have a higher film temperature, you will have more coking. So 26-degree rise in film temperature will double your coking rate. That's generally the industry thumb rule. Lower velocity will cause you higher film temperature and leading to coking. So these are very simple things, but I still wanted to give it to you before we talk about. Let's talk about a heater, which is pressure drop limited. It's a 2-pass heater. Very simple flow scheme I have done. Now you want to increase the charge rate by 20% or 25%. And conventional will be, let's increase either the number of passes or increase the tube size. And both those options are very expensive. And what we have come up with a solution is whatever charge rate you want to increase 20-25%, let's take it and put it in a separate pass and make it at the outlet. And that is what our patented technology or the split flow is. We leave the most of the heater as it is. We do some surgery in the convection section. And by doing that, we are able to increase or reduce the pressure drop, or even you can say increase the capacity. Either way, we are able to achieve it. So very simple concept. We are able to control the flow rate and basically make sure that the outlet temperature of the split flow and the main flow is the same. So very simple concept, but it has been very effective. We have almost like 12 installations. So let me talk about our first case study. This was in a refinery in Texas. And this is a horizontal box type natural draft heater, 45 million BTU, 72% thermal efficiency. The allowable pressure drop was 90 psi. It was a 2-pass heater, box heater, built in 1975. And this is a cross section of the heater, stack, convection section, radiant section, as you can see over here. So the radiant section consisted of 28 tubes, 2 rows of roof tubes, and the tubes were 5-inch size. The convection section consisted of fin tubes in 6 rows. 2 rows of bare tubes was in this thing, and these were 4-inch size. So the convection had 4-inch tubes, the radiant had 5-inch tubes, pretty standard configuration. This is the other view of the heater, very small convection section, and then a damper, a stack and a damper on the top, burners at the floor. So the average operating duty of the heater was much low, but the charge rate was almost 32% higher as compared to the design. So the pressure drop across the heater went up to 150 psi. And the client wanted us to evaluate and say, hey, can we do 4-pass heater or any other option? And they wanted to reduce the pressure drop to 50 psi. So from 150, we had to go down to 50 psi. So that was the project given to us. We did a study on the heater and we came up with 3 options, I should say. We said, okay, we can take your heater and make it a 4-pass heater, leaving the tube size as it is. And that is one option, but it will need complete retubing. Or the second option is we increase that, leave it as a 2-pass heater, but we increase the size of tubes to 5-inch in the convection and 6-inch in the radiant. So basically you will need a new radiant coil, new tube supports, and a new convection section. So these were the 2 options which were conventional approaches. And you can see over here, this is basically how the existing heater is, 2-pass heater, inlet outlet, convection radiant, and then you make it a 4-pass heater. You can see it over here. So very simple conventional arrangement. Now what you have to see is when you do a 2 to 4 pass, your pass length becomes half and your mass velocity goes down by 50%. So as a result, your pressure drop went down to 22 from almost 1/8. From 150, we went down to 22, 22 less than 50 what they need. So this is a very technically acceptable option. Nothing wrong. And the second option was increasing the tube size. And here also we were able to reduce the pressure drop from 150 to 40. This is a 4-inch tube, this is a 5-inch tube, but you basically are looking at a very expensive this thing. So these were the 2 options, and after looking at the cost, we said, okay, either you go for a 4-pass design or you go for a split flow design, 3 passes. So that is what basically we said. You can reduce down to 22 psi. There were some minor changes because you had to do 4 pass, so we were going to add 2 tubes. And this modification was costing about $2.5 million, and our estimate was plus minus 30%. So, and the client was ready to proceed with this. The client was ready to spend this amount of money because that's what they were working with an E&C company. And they said, okay, let's convert this heater into a 4-pass heater. And what we then came back and said, hey, we can convert your heater from 2-pass to 3-pass using our split flow technology. And the 2 passes in the convection will be connected together and they will become a single pass, single split flow pass. And we will have 23% of the flow going through that convection section. 77% of the flow will go directly into the radiant section. And existing heater coils are retained. And by doing this change, we were able to get a pressure drop of 49.6. You may think I'm fudging, but no, this is correct. They wanted 50, I made it 49.6, and it still had 5 pounds margin. So, and that's basically what it was. We took 22% flow, 78,000 pounds, put it in the convection section, took it out, and rest of the flow went through the convection radiant sections in 2 passes. And when we did that, everything included, including our fee modifications, there were no modification in the heater. The cost was about 660%. So basically 1/4, I would say, 1/4 of the conventional cost. And we were able to convince the client that you convert the convection section into another pass by converting by adding a jump over, and it becomes like one pass. So all the modification was external to the heater. There were no modifications done internally to the heater. And this project is being executed now, should be in operation in about, I would say, another couple of months. And you can see all the modification, the pipe, it was only piping modification. What you see in blue, that's all the piping that was done by us. So very, very simple modification. And there was no modification in the heater. The client was surprised actually that how could you do that in such a low cost? And we still ended up making money. It's not that we suffered a loss, but we were able to save client almost $1.9 million actually. So the second case study is from another job which we are doing right now. So this was an air heater, very small air heater, 11 million BTU, uh, vertical cylindrical natural draft. It was supposed to be heating process air. The allowable pressure drop was 14 psi. Uh, 2014, they did a revamp. They upgraded the tubes from schedule 40 to schedule 120. And this is the heater, pretty small heater. This is a small convection section they had, bare rows and finned rows, pretty standard convection section. And then their requirement increased from 78,000 pounds of air to 97,000 pounds of air in 2020. We don't know why, but that's what happened. And then the operating pressure drop became from 15 to 28. And this created a bottleneck in their compressor system. They wanted pressure drop to be reduced back to 14 psi. And we had a turnaround time of 25 days to do it. So we worked with the client and we wanted to give them solutions. So the conventional solution was converted into a 4-pass, or the other option was using 3-pass design of our split flow. So 4-pass design can be done. The pressure drop comes down to about 3.5, no problem. I mean, this is again the same thing. And that's a simulation by our team. So everything works out. Only the efficiency loss is there by about 2%. But we are able to match all the requirements. And this required a very large cost, almost close to about 800,000 US dollars. And this is how this whole thing will be looking like. And then we gave them a cheaper solution. Let's convert it into 3-pass. So the first solution we gave them was converting the conventional split flow, whereas we take the convection section and convert it into split flow by conjoining the 2 passes in a series, and then the 2 passes in the radiant are used as existing. 25% of the process air goes into the split flow pass. And it was working very good. You can see I'm getting the same duty. I'm able to reduce the pressure drop to about 13.7. But what we saw was that the flue gas temperature went up by 100 degrees. So the client was losing about 3%, 3.5% efficiency. So we were not satisfied with this solution. We said, hey, let's think about it and come out with a better solution. And this happened because of approach, because of higher temperature in the convection section. So the convection heat transfer efficiency dropped down. So then we said, okay, let's do something else. This was the conventional route, connecting the two passes in the convection and make it a split flow. So we came up with another design and we said, let us create a split flow in the radiant coil, in the radiant section. So we created two passes in the convection and radiant as it is. And then we create one pass, one half of the radiant coil as a split flow pass. So 35% goes into the split flow pass and 65% goes into the other two passes. So it's almost one third, one third, one third, almost one third. And we were able to reduce the pressure drop again from 28.4 to 12 psi. Thermal efficiency remained the same. So we were able to achieve, same almost thermal efficiency and lower pressure drop, So this project also was executed at a much lower cost. No modification to the heater coils, only inlet outlet piping modifications. Estimated cost about $150,000 plus minus 30%. And this will be executed this year. And we will let you know how it works. But that's what our this thing. So the two cases which I presented to you where we reduced pressure drop did not involve any heater internal modification. We were able to execute the job just from external piping. The next case study I am presenting to you is a very interesting case study. This was a heater in one of the Texas refineries. Most of the work, what we do in US, although it is all over, but we do a lot of work in Texas. And this was a reactor charge heater and 30 million BTUs. Convection section was used for waste heat recovery. They had a steam drum and they were generating steam, So this is a picture of the heater. You can see they put a waste heat boiler afterwards, so you can see all this external structure here. Burners on the bottom, 6-inch tubes at 18-inch pitch. And this was a high pressure heater, so pretty high schedule 120 tubes, stainless steel tubes, length of 50 feet, bridge wall in the center, burners right over here, two pass arrangement, 12,000 flux, Convection section was basically waste heat recovery, you know, steam generation coils, steam superheater coils, boiler feed water coils. So approximately, I think total heat duty was 13 plus 1, 14, 18, 19 million BTUs was what they were absorbing in the convection. So the heater flow scheme was like this: 611 inlet, 805, 62.5 psi pressure drop, And we checked it. So most of the time when you work with us, we will check the original design. So we match the original design, of that heater to make sure that, hey, we are getting what they are saying, And then they said, hey, we are increasing the capacity. So we want to reduce the pressure drop from 62 psi to 25 psi, almost 60% reduction in pressure drop. They wanted to increase the heater duty also 37 million BTUs. And they had a limitation that EPA said no more than 54 million BTUs an hour actually. So these were the three limitations they gave us, three parameters: increase the process duty, reduce the pressure drop, and improve the efficiency or limit the firing to 54 million BTUs. Very challenging project. and they were working with an E&C company, and the E&C company or EPC company said, hey, this is not possible to do with the existing heater. Let's go and buy a new heater. So they went and got a quote, and the total installed cost of the new heater was about $6.5 million, because you need the foundations, you need steel, you need piping, you need instrumentation. So the heater cost goes up tremendously, even though the heater may be costing about 1.5 or $2 million. By the time you install it, the cost triples. So they almost went in for a new heater. And to be honest, everybody likes new heater except the owner, because they are spending a lot of money. So the project went to the board, and the board, there were some technical people, and they said, hey, have you talked to furnace improvements? And they said, no, we are not talked to the furnace improvements. We are working through an EPC, and they have already discussed this with other heater vendors. So we want to go for this. So they came back and they said, board said, why don't you talk to furnace improvement? So the project manager, the client's project manager, called me and said, hey, we have this job, we want you to have a look, and I want to get it done in a week. We said we normally need 6 weeks for a study. He said, I want to get it done in a week. So I said, okay, well, let me look it over. So we looked it over and we said, hey, we can save your heater actually. Our finding was that we can save your heater. You don't need a new heater, and we will do this whole job: design, engineering, supply, installation, for about 1.1 or $1.2 million. That was a number we gave him at that time. And after checking our design, checking our philosophy, they said, okay, go ahead and do it. So we did this job for $1.2 million, saved client almost $5 million. And this was the new parameters which they gave us. They said pressure drop has to be less than 25 psi. And the conventional routes, we always give them the conventional route for the options also, because when we do study, we want to tell them, we want to be open with them and say, hey, these are the conventional options and these are our options, patented option. So compare, let's have an open book approach and compare. So this was a radiant section retubing option we gave them, which means complete new radiant coil and complete new convection section. That was one. This is how it looked, the heater looked. So you can see how the new coils would have looked like. And it would have reduced the pressure drop down to about 15 psi. So technically it is fine. I mean, this was worked this thing. So technically it worked fine. So this is the performance of that heater. The cost was about $2.2 million. That was the second option of retubing with converting it into 4-pass. And this is how that option would have looked like. And again, the cost was almost same. It would be 21 psi pressure drop. You can do it. But again, the cost was about $2.5 million. And then we came up with a split flow. And we said we will only replace the convection section using our split flow. And instead of having the waste heat recovery, we will have process and waste heat recovery. So we put 3 passes. 2 passes went into the radiant, 70% flow and 30% flow went into the convection section. And then we had a waste heat recovery coil also designed there, so which worked. And this is all what we did. So this is the convection section we did, and we were able to reduce their stack temperature also drastically to 533. This is how, this is all what we did. This is how the existing heater looked like. We took their waste heat recovery section, put our split flow convection section, and boom, the heater started working. So if you see the split flow, this is basically 3 passes, very conventional heater. 2 passes have 35% flow, and the third one, the split flow, has 30% flow, and we control it by TIC. So what we are doing is we are balancing the heat transfer and pressure drop. So what happened? Oh, yeah. And this is all what we did. This was before revamp, and this is the new convection section after revamp. And we did little bit of modification and the radiant section here, but nothing internal, nothing internal, only external. So there was a little bit of modification here. And we were able to reduce to 20 psi. Pressure drop came down 20 psi. We were able to limit their firing also, you know, and get the efficiency. The duty they wanted 37, we were able to get them 37 process duty. So we were able to do that, and basically the job was completed at about 50% of the conventional cost, even more, and a lower shutdown time. This is the 3D model of that furnace. So this is a picture of the convection section being fabricated. You can see this is the waste heat recovery. This is the split flow coil. So very simple, conventional. So these are our references we have done for different clients, about 12 or 13 references what we have on split flow, where we have reduced the pressure drop, increased the capacity, all those things, improved efficiency. We have used the split flow for various purposes. And Delec likes our technology because they have been able to reduce pressure drop. They have specifically focused on pressure drop, so they like our technology. We have installed them in about 4 heaters. And these are some of the advantages of our technology: lower pressure drop, higher efficiency, you can run higher capacity, lower firing rate, and the most important is lower installation cost. So the first point and the last point are the most important benefits of the split flow. The project managers will like it very much. So thank you very much. Uh, let us know if you have a heater where you want us to work on, and we will be more than happy to help you out. If you have a heater which is pressure drop limited, and also if you have a heater which is giving you trouble, I normally tell my clients, give us the worst heater and we will make it the best heater. So thank you very much for your time. And let me see if we have any questions. Okay, I've got two. Is this split flow acceptable as per API? Yes. I mean, we have talked to them and there is nothing, uh, this going against this thing. So they say that the passes should be symmetrical, but our passes, the split flow is not symmetrical, but that's the only thing, but it is fine. And let me see. So we have a question from another this thing. It talks about we have a fired heater facing problem of high burner tip pressure when increasing fuel. Will blowing a fuel line will help reduce the burner tip pressure? I think you have to clean the burner tips. When you clean the burner tips, the fuel gas pressure will come down. So please clean your burner tips. That will help you. Blowing the line may help you, but I don't think, because uh, tip plugging is a more common occurrence than fuel gas line plugging, but you can try both actually. So we don't see anything, any issue there. Anybody else has any question? Otherwise, uh, thank you all for listening, and wish you all the best. Hopefully we'll see you again on a different topic. We want to share all our yes, Prabhat, if you have a question, can you put it down? I'll be more than happy to write it out, or I will contact you separately. Yeah. So again, thank you very much for giving us a patient hearing. Bye.